Mr. Antonucci here, and we're going to discuss increasing and decreasing functions in this video. First thing we need to talk about is increasing and decreasing function test. So we suppose f is a differentiable function on the open interval a to b. If f prime of x is greater than 0 on the open interval a to b, then f is said to be increasing on the open interval a to b. And if the derivative is less than 0 or the derivative is negative on the open interval, then f is decreasing on that open interval. Questions about where a function is increasing or decreasing are extremely common on both the multiple choice questions and the free response questions on the AP exam. Now, before we get into some of the examples, there are some important considerations about the increasing, decreasing function test. When using the test, we determine the open intervals on which the derivative is positive or negative. Also, if f is continuous on the closed interval a to b and differentiable on the open interval a to b, then if the derivative is positive on the open interval a to b, then f is said to be increasing on the closed interval a to b. This is important because it tells us that we're allowed to include the endpoints in our interval. Similarly, if the derivative is negative on that open interval, then f is decreasing on the closed interval a to b. Also, the increasing, decreasing function test is valid on different kinds of intervals. It's valid on the open interval a to b, but it's also valid for intervals involving infinity, like negative infinity to b, a to positive infinity, and negative infinity to infinity. Again, this is assuming that the function is continuous and differentiable on these intervals. Now let's get to an example. We want to determine where this function is increasing and decreasing. Since the function's a polynomial, we know f is continuous and differentiable at every real number. So the first thing to do is find the derivative. So according to the increasing, decreasing function test, f is increasing on the intervals where the derivative is positive and decreasing on intervals where the derivative is negative. So we can use that information to solve inequalities involving the first derivative. The first thing to do, however, is to set the derivative equal to 0 and then solve for x. Factor out a 6 and then factor the polynomial. And then we get x equals 2 and x equals 1. Once we know where the first derivative is equal to 0, we can then set up intervals, because by the intermediate value theorem, the function is not going to change sign unless it passes through 0. So we could just make a sign chart. So x equals 1 and x equals 2. And then what you could do is you pick a number before, between, and after each point and test it in the first derivative, because that point is representative of the sign of the first derivative. So if I use, say, x equals 0 here, f prime of 0, I'm not so much concerned about what the numerical value is as I am with the sign of the derivative when x is 0. If I use the factored form, I would just have 6 times -2 times -1, which would make a positive. So I know that the derivative is greater than 0 at 0. That's indicative of this entire interval for x less than 1. So I know the derivative is positive. If I pick a number between 1 and 2, let's say 1.5, then f of 1.5, if I use the factored form again, I would have 6 times a negative number times a positive number, which is going to make a negative number. So that whole interval, I know the first derivative is negative. And then last, we'll pick a number after 2. I like to try to pick easy numbers. If I plug in 3 to the factored form, you would have a positive there. So I know on that interval, the derivative is positive. So our conclusion is that f is increasing on the intervals negative infinity to 1 and 2 to infinity. And now here's the justification, since f prime is greater than 0 on these intervals. Then we know f is decreasing on the interval 1 to 2, since f prime is less than 0 on these intervals. Using Desmos, I can quickly graph the function and verify the intervals of increase and decrease. Notice that the function is increasing before 1, and then between 1 and 2 on the x-axis, the function is decreasing, and also after x equals 2, the function is increasing again. Additionally, I can graph f prime and verify that the first derivative is positive for values less than 1 and values greater than 2, and the first derivative is negative for values between 1 and 2. And one other thing that's interesting to point out is that the intervals where the derivative is positive, the blue function, the original function, the red one, is increasing. And the intervals where the blue function, the derivative, is negative, has negative values, the original function is decreasing. It is true that f is increasing on these intervals because the first derivative is positive, but also since the original function is continuous, we can include the endpoints of these intervals on the intervals of increase and decrease. So we could put a bracket here, bracket here, and here. Here's another way that a question might be asked. The first derivative of the function f is defined by f prime equals cosine of 2x squared minus 1 for x between 0 and 2. On what intervals is f increasing or decreasing? Notice this is a Desmos allowed question. Now you have to be careful here because they're asking you questions about the original function f, but all we know is the first derivative. But we know the increasing, decreasing function test only uses the first derivative. So here I've graphed the function in Desmos, and I've called it y equals instead of setting it equal to f prime because we just need to graph the function. If I set it equal to f prime, that's not going to work. Also, I've restricted the domain to be from 0 to 2, so I'm only looking at the picture that the question is asking about. Since I know that the derivative tells me when a function is increasing or decreasing, I can quickly see that the derivative is positive from 0 up to a little after 1 right here. And I can export that point. And then it's negative between that point and the next one. And then from there, the derivative is positive again. So these are the 2 points which are going to define my intervals. So I would have 2 intervals where f is increasing and 1 interval where f is decreasing, which is between those 2 values. So when answering the question, we can say that f is increasing on 0 to 1.134 and 1.69 to 2, since f prime is positive on those intervals. Then we could also say f is decreasing on the interval 1.134 to 1.69 since f prime is less than 0 on those intervals. Since the derivative exists for all values from 0 to 2, that means the original function is continuous. Remember, differentiability implies continuity. So we can include the endpoints on the intervals for increasing and decreasing, making all of these brackets. So here's another one where we have to determine whether the function is increasing or decreasing. F is continuous for all real numbers, and so we could get the derivative by using the chain rule. So 2/3 times the derivative of the inside. And this is going to simplify to 4x over 3 times x squared minus 1 to the 1/3. One thing that's very important is that f prime does not exist at -1 and +1. So the domain of f prime is all real numbers except -1 and 1. Also, f prime is equal to 0 if the numerator of the function is equal to 0. So 4x is going to equal to 0 when x is 0. So there are 3 critical values here, x equals 0 and x equals plus or minus 1. And the increasing decreasing function test states that f is increasing on intervals where the derivative is positive, decreasing on intervals where the derivative is negative. So these 3 values are going to split our intervals to test on. So -1, 0, and 1. And then we just test a value before, between, and after each of those critical values, and we plug that into the first derivative. So something before -1, we would test, let's say, -2. The first derivative is going to be negative at that value, so this entire interval is negative. Then we pick a number between -1 and 0, like -1/2, and the derivative is going to be positive for that value, so we know that the function is going to be increasing there. Then we pick a value between 0 and 1, so 1/2, and we know that the derivative is negative there. So the function is going to be decreasing on that interval. And then finally, we pick a value after 1, let's say 2. We plug in 2, the derivative is positive. Now, if you notice here, these alternate negative, positive, negative, positive. It doesn't always work out that way. So just be careful not to make the mistake that assuming once you know the first sign, you can just alternate them from there. So now we have our intervals. And since f is continuous on its domain, it's increasing on the intervals -1 to 0 and 1, infinity. F is decreasing on the intervals -infinity to -1 and 0 to 1. So again, here's the graph of f. You can verify that it's decreasing on the interval -infinity to -1 and 0 to 1, as well as increasing from -1 to 0 and 1 to infinity. Additionally, we can quickly graph the first derivative and see that the blue graph is negative where the original function is decreasing and positive where the original function is increasing. So here's another example. Determine where the function f of x equals x squared e to the x is increasing and decreasing. Again, note f of x is continuous and differentiable for all values of x, so we can use the increasing decreasing function test. First thing we want to do is take the derivative. So product rule, derivative of the first times the second plus the first times the derivative of the second. Remember, derivative of e to the x is itself. Then we can factor out an x and an e. So the critical numbers that we're talking about in this problem are values that make the derivative 0 or undefined. That would be at x equals 0 and x equals -2. There are no values that make the derivative undefined. So there are going to be 2 breakpoints in our number line, namely at -2 and at 0. Then we pick a number before, between, and after and test it in the first derivative. So if I pick any number before -2, like -3, and test it in the first derivative, you would get a positive value. That means that f is increasing on the interval -infinity to -2. If I pick a value between -2 and 0, like -1, and I test it in the first derivative, it's going to be negative. That's going to imply that f is decreasing on the interval -2 to 0. And lastly, it can test a value after 0, so 1, in the first derivative, and it's positive. So that implies that f is increasing on the interval 0 to infinity. However, this is not our final answer. This is the conclusion that we make from the first derivative. Since the function f is continuous on its domain, we can include the endpoints of these intervals that are not infinite. So namely, f is increasing on -infinity to -2, including -2, and 0 to infinity. Make sure you include the 0. F is decreasing on the interval -2 to 0 inclusive. Another type of question that often comes up is analyzing the graph of the derivative in order to find out information about the original function. And this is where we have to be very careful, because in this example here, you're given the graph of the derivative f prime and asked information about f. Also, it's important to read the context carefully because sometimes they give you information that is very critical to be able to answer the questions. So for example, the graph of f prime, the derivative of f is shown. It is known that f is continuous for all real numbers. That's going to be important for stating our answers. Answer the following. What is the domain of the derivative? Well, the derivative, as shown in the graph, we can see that it's defined for all numbers except x equals 0 and x equals 2. Then part B, for what values of x does f have a horizontal tangent? Well, the graph of f has a horizontal tangent line when the derivative is 0. So that would be at x equals -2 and x equals 4. The justification is what I just verbally stated. We have a horizontal tangent line when the derivative is 0. Part C, for what values of x does f have a vertical tangent? The vertical tangent is going to occur when the derivative is unbounded. So x equals 0. And our justification is that the derivative is unbounded at x equals 0. Part D, for what values of x does f have a corner? Well, from the graph of f prime, we can see that at x equals 2, the value of the derivative changes abruptly from 2 to roughly 1. So these unequal one-sided limits of the derivative as x approaches 2 imply that as x approaches 2 from the left and right, the derivative has different values. So this means that the graph of f has a corner at x equals 2. And then finally, what intervals is f increasing? Well, f is increasing when the derivative is positive. So -2 to 0, 0 to 2, and 2 to 4. However, since f is continuous for all real numbers, we can include the endpoints of those intervals, and really, it's going to be increasing on the interval -2 all the way up to 4, including the endpoints. And then f is decreasing for values where the derivative is negative, namely -infinity, -2, and 4 to infinity. But again, since the original function is said to be continuous, we can include the non-infinite endpoints. So -infinity to -2 and 4 to infinity. So you might be wondering why we can include both -2 and 4 in the intervals of increasing and decreasing. A simple explanation is that functions increase and decrease on intervals, not at points. And strictly speaking, a function is increasing if you move from one x value to another x value, the y values become greater. So as we move from -2 to 4 on the x-axis, the y values continuously get greater as you move from 2 to 4, including that last point when x is 4. A function is decreasing if when you move from one x value to another, left to right, the y values decrease. So let's look at investigating some particle motion. An object moves along the y-axis with velocity v equals v of t, where t is measured in hours and v of t is measured in meters per hour. The velocity function is a differentiable function for t greater than or equal to 0, and the object is at the origin when t equals 0. The table below shows values of the velocity at certain times. So A, show that there are at least 2 times at which the velocity of the object is 0. Now, for part A, since the velocity function is differentiable for t greater than or equal to 0, the function v must be continuous on the interval 0.2 to 3.8. So if we use the intermediate value theorem, since v of 0.8 is greater than 0 and v of 1.5 is less than 0, there must be at least one time between 0.8 and 1.5 for which v of t is equal to 0. Similarly, if you look at the interval from 1.5 to 2, you have a sign change in velocity. So I know that v of 1.5 is less than 0 and v of 2.0 is greater than 0. Now, this all hinges on the fact that we know that this function is continuous because they said that the velocity function is a differentiable function. So if you're asked this type of question on a free response, you have to justify that the conditions for the intermediate value theorem have been satisfied so that you can use its conclusion. And you also want to state specifically that you use the intermediate value theorem. So because there is a sign change 2 times on this interval of a continuous function, we know that the velocity function had to equal 0 at least 2 times. We don't know exactly what happens in between, so that's why we say at least 2 times. For part B, we want to show that there's at least one time at which the acceleration of the object is 0. If I look at these 2 points right here at 0.8 and 2.0 hours, notice they have the same velocity. So since the velocity function is differentiable for t greater than or equal to 0, the function is continuous on the interval 0.8 to 2.0. This means that the velocity function is continuous on a closed interval, differentiable in between, so the mean value theorem applies. Again, if we're going to use the mean value theorem, we have to show that the conditions are met in order to make the conclusion. The mean value theorem just says that the average rate of change of a function is equal to the instantaneous rate of change of the function for some time in between the endpoints. So we could do v of 2 minus v of 0.8 all over 2 minus 0.8. V of 2 is 5. V of 0.8 is 5. The denominator is going to be 1.2. And this is going to simplify to 0. So by the mean value theorem, there is at least one time t in the interval 0.8 to 2.0 for which the acceleration is equal to 0. Okay, one last application question. The function f models the yield of a plant measured in bushels for a certain amount of fertilizer X. For what values is the plant yield increasing or decreasing? Justify your answer. So the yield's going to be increasing when f prime is greater than 0, and it's going to be decreasing when f prime is less than 0. Since we are allowed to use Desmos, we can do most of this in Desmos. So here we have the graph of the plant yield function. Now be careful here because it does change sign right here. And it would be tempting to say that it's positive before this and negative after, which is true about the function. But remember, this is the original function. In fact, for values after 3.896, this function doesn't make sense in the context because you can't have a negative plant yield. So what we could do, however, is graph the derivative. It's in green here. And note where the derivative changes sign. If you look at the home screen, it looks like, if I zoom in a little bit, that it changes sign at 1. But if you zoom in a little bit more, you can see that not exactly at 1. It actually changes sign at 1.043. So that's another thing we have to be careful about is when we're using Desmos to investigate the graph of a function, there can be subtle little differences that you can't see until you zoom in. So this is the point where the derivative changes sign. So the plant yield is going to be increasing before this time because the derivative is positive and decreasing after because the derivative is negative. So the derivative is positive for x less than 1.044 and is negative for values greater than 1.044. Now, given answers that make sense in the context of the problem, we could actually use x between 3.896 and 1.044. Because remember, we talked about how the model doesn't make sense for values of x greater than 3.896. All right, guys, that's it for increasing and decreasing functions. Hope that was helpful to you. Please do subscribe to the channel, like this video, and drop me a comment letting me know what was helpful to you. Take care.